So in the last two sessions we had seen unit 2, which is signal degradation of optical fiber. Degradation, which is your attenuation in terms of absorption loss, scattering loss, bending loss, which is micro bending and macro bending loss, then core losses of the optical fiber, which we had seen in the last week. Then the signal distortion in optical. Okay. So we have defined the group delay characteristics, the derivation for group delay, the two different types of dispersion, so which is material dispersion and waveguide dispersion. So then we had derivations and equations with relevant graphs for material dispersion. So in today's session, we are going to the intermodal dispersion. Okay, so let us move on to that. And we are going to see pulse broadening in gradient index fibers, followed by the design of and multimode fibers, which is used for mode coupling of optical fiber. Hope the presentation is visible.
Yes, sir. Visible, sir.
Yes, sir.
Yeah, okay. Thank you for your valuable feedback. So let us start the intermodal delay or the intermodal distortion. So this intermodal is mostly in multimode fibers. Why? Because here different types of modes are operating at different wavelengths or at different velocities. If we have a TE0 mode, TE1 mode, TE2 mode, TE5, all these modes will travel in a single fiber. So which is the basic of a multimode. Okay, multimode in the sense many modes will in a single optical fiber. So that too in a step index fiber, each mode, each and every mode will have different velocities. So mode 1 will be traveling in velocity 1 at a wavelength lambda 1. Second will travel at with wavelength lambda 2, and so on. So when moves in a single optical fiber, there is a chance that the due to this in a single fiber, intermodal delays will occur. Surely it will occur. How it occurs is that it depends upon the lower order modes and the higher order modes. The higher order modes, which are propagating the optical fiber with a slower axial group, resulting due to the steeper angle of propagation. The higher order modes will travel slower than the lower, means that TE 1415 will make a delay as compared to TE1 and 2. For example, the lower order modes are TE0, TE1, TE2, TE3, TE5. The higher order modes are TE11, TE13, and so on. So when the higher order modes and the traveling in a single optical fiber cable, the higher order modes travel a bit slower than compared to the lower order modes. Receiver, the lower order modes will be received, and the higher order modes will be received at the receiver at a slower delay. So this causes intermodal delay, leading to a factor called pulse broadening or pulse. So how do I delay is sigma mod mode intermodal, which is equal to T maximum minus, which can be obtained by N1 effect index of into the index difference into L length of the fiber divided by C. This is the formula for finding intermodal delay. So due to this intermodal delay, we get pulse spreading. Okay, so let us see how it is. See, there are A, B, C, D. Let us see A. So A is the input pulses which are given at your transmit. Okay, A. So you can see that the first pulse and the second pulse. You can able to distinguish them easily. When you see B, distinguishable pulses at time T2 greater than T1. Okay, T1 represents this instant, T2 represents this instant. When the pulses up with T2 greater than T1, so this would be pattern of pulse broadening. You can see that here. The pulse which should go like this, it should rise and fall like this, but it is rising, falling an extent, then it rises again. So here you can able to distinguish between the first pulse and the second pulse, but when it barely distinguishable pulses at time t2 greater than that, at the outputs at the outputs, signal rises and falls only for a shorter period, and the second rises and falls. So here is the occurs. So the first input pulse and the second input pulse overlapped. So due to this, intersymbol interference occurs depending upon the distance of the fiber, okay, length of the fiber. So this is difference. So, but this we can distinguish. So how much time interval this was being symbol that can be easily identified. So whereas the fourth or the D, indistinguishable pulses at a time which are greater than time t4 greater than t3, t1, t2, t3, t4. So when you see this, the first pulse, so it is rising, it is falling at a very and rising immediately, and it's falling. So here you can see that more interference as the distance of the fiber increases. This leads to pulse broadening. So you can see that the pulse here at this point pulse is narrow, at this point pulse is expanding, here pulse is expanding, but here it is morely expanded, so which is pulse broadening. So which leads to spreading of your optical signals, which can be called as EMD. pulse mode dispersion. So the effects of fiber to agents on the polarization states of an optical source of pulse broadening results in pulse mode dispersion. Okay. So the effects of the optic the pulse one due to the bi second pulse due to this we call it as polarization mode dispersion. This is due to slightly different velocity for each polarization mode because of the lack of perfectly symmetric and anisotropicity of the fiber. So if the group velocities of two orthogonal polarization modes are given as Vgx and Vgy, the differential time delay will be del code. Okay, total polarization can be calculated by dispersion in the mode dispersion, which can be calculated by L divided by Vgx minus L divided by Vgy, which is L divided by length is the L, uh, which is the length of the fiber or the distance between the transmitter and receiver for which this PMD occurs. Vgx is the one of the orthogonal polarization mode and V is the orthogonal polarization modes velocity. So this is how to determine polarization mode dispersion. So here you can see this is your transmitter, this green here at left side is your transmitter where it is given as your input pulse, and this yellow color is your core fiber. In an optical fiber we have the inner, so with the refractive index n1. So at this point it is measured as x, and this point is measured as y. So x in this direction, y in this direction. So all light when it falls onto the optical fiber, it propagates in and towards the receiver. So using the coaxial along the axial of the fiber, along the axis of the fiber, it propagates to the electromagnetic wave that propagates in cylindrical. Okay, so it propagates. So here of electric as well as Ex Ey direction. It propagates along the core. So at the out on the distance, the time pulse, okay, the narrow time pulse will resemble like this, broadening. So suppose that the core refractive index has different values along the directions that corresponds to the electric field oscillation direction or the polarizations. X-axis and y-axis along these directions. And input light will travel along the fiber with the EX and polarizations having different group velocities. At the receiver, they obtain mode dispersion. So the pulse broadening obtained at the receiver is called as pulse mode dispersion. So the next dispersion that we are going to see is the chromatic and total dispersion. So chromatic dispersion the material and waveguide dispersions. Okay, the dispersion to the material and dispersion occurred waveguide. So which is chromatic dispersion d of lambda is approximately equal to the absolute value of material dispersion plus waveguide dispersion. So which is CH is equal to dCH of lambda into L into sigma. So then we can find the total dispersion, which is the sum of chromatic dispersion as well as the pulse dispersion and other types of dispersions. So which can be given as d total approximately equal to the modulus of dCH plus depolarization and the pulse spreadings and other dispersion types. Can be given as sigma total is equal to d total over the length sigma of
Excuse me, sir.
lambda. So here is a for total dispersion measured
So slides are
for
not
the
moving,
wavelength.
sir. And now it's moving, sir.
Yeah, now
No, sir. Total dispersion. Same slide is there.
how is it
Not
visible?
moving. Visible, sir, but not moving, sir.
What slide you are able to see now? Chat box.
Total
Total
dispersion, zero
dispersion and
dispersion.
zero
40
dispersion.
seconds, sir. 40 seconds,
Yeah,
sir.
yeah, this slide only. Yeah, this slide only. Okay. So after the chromatic dispersion calculation, which is chromatic dispersion can be obtained by the summation of the dispersion and waveguide dispersion. And the total dispersion is the sum of chromatic dispersion, pulse mode dispersion, and the other dispersion if available, and the total root mean square pulse, the pulse spreading signals. So which can be given as L is equal to the chromatic dispersion plus polarization dispersion and the remaining absolute value of that, which can be written as sigma total is equal to d total length L sigma lambda. So this total dispersion and the zero graph is taken for about 300 nanometer and 1550 nanometer, which is second window. 1300 nanometer is second window. 550 nanometer is the third window. So the same diagram we had seen in previous class. I'll show you. Yeah, this one. It is the same. In terms of dispersion, we had drawn it here. You can see dispersion of material is given as dmat 0 dB crossing. So it is crossing at the desired dispersion where zero dispersion occurs, and here it is crossing 1270 as a function of wavelength measured in nanometers. These are measured in nanometers. So the same diagram but illustration in black and white. So that is the difference. So this is your total dispersion. This is your 0 decibels. Okay. There is 1200, 1300, 1400, 1500, 1000. To show that where you can see that here the material is 0 almost at 1270 and the total will be nearly 0 at 1310 nanometers. Same diagram which I had shown you, same graph. Here it is in black and white, there it is in color. Difference. Designing a single mode fiber and its attenuation characteristics is a major challenge nowadays. So we need to a fact we need to understand a fact that while designing a single mode fibers, consider which is minimum distortion is at a wavelength of 1300 nanometer for single mode fibers always, which is using silica fiber as the material. And the second fact is that attenuation. Keep in mind minimum distortion at 1300 and minimum attenuation is at 1550 for single mode. So depending upon the requirements, shift the zero dispersion to longer wavelength. It is having a minimum attenuation and dispersion by modifying the dispersion. The waveguide dispersion from a step index core profile to more complicated profile. If you do that, we can easily design a single mode file and use it for communication with distorted signals and a minimum attenuation. Seen it for the single mode fibers, the minimum distortion is around 100 and the attenuation is obtained only at 1550 nanometer, which is the second window and the third window. So if you make a of the fiber such that dispersion is modified from this profile to a more complicated profile, then obviously we'll get single mode fibers. So how do we do is that there are 4 categories to do this. One is using 1300 nanometer step index fibers with a match of having a mode diameter 9.6 micrometer, depressed cladding 9 micrometers. So like this you can choose the fiber which has dispersion shifted fibers as well as flattened fibers. This can be chosen. Next is large effective area, which is typically be greater than 100 micrometers. 100 square micrometers. If it is like that, then you can easily design an efficient single mode step index fiber. Keep in remembrance mode diameter 9.6 micrometer, 9 micrometer, having larger effective area with a cross with the effective cross section of about 100 square micrometers. So this is the design of the single mode fiber dispersion. You can see the material dispersion is this, which comes to 0 around 1270. The dispersion shifted. This is the characteristics dispersion pattern and 1300 nanometer optimized. So these all get dispersion. So keeping in mind, you can see that the dispersion or the attenuation, whether the shifted or flattened, is very at this place. Whereas material place. So depending upon this, you can design an efficient single mode filter. This is dispersion versus wavelength, another curve. The 1300 nanometer is an optimized path. This is the curve for the dispersion flattened. This is the curve for the dispersion shifted. So how do I calculate this? Is that by using the fundamental modes with 0.405 and lambda being calculated as v square root of n1 square minus n2 square. And the dispersion formula we all are familiar, is equal to d tau divided by d lambda, which is material dispersion plus waveguide dispersion over the wavelength. So for a non-dispersion shifted fibers, wavelength to be used stands around 1270, 1340, whereas for dispersion shifted fibers, we can use 1500 nanometer to 1600 nanometers. So like this we can use depending upon the application. The formula for the non-dispersion shifted fibers is T of lambda is equal to T naught plus S naught by 8 lambda minus lambda naught square divided by lambda the whole square. So a T relative delay minimum at zero dispersion having lambda naught, and S naught is the value of the dispersion measured in or nanometer square per kilometer. So S naught can be obtained by lambda naught minus dd divided by lambda is equal to lambda naught. So for the non-dispersion shifted fibers, dispersion can be obtained by T of lambda is equal to lambda into S naught by 4, 1 minus lambda naught the whole power 4. Next is the dispersion for a dispersion shift operating at 1500 to 1600 nanometer. The form lambda is equal to T naught plus S naught by 2 lambda minus lambda naught. A dispersion can be obtained as d of lambda is equal to lambda minus lambda naught into S naught. So these are the example of a dispersion performance curve for a set of fibers. The graph is taken for a wave dispersion, wavelength measured in nanometers, dispersion is measured in picoseconds per kilometer. We have the zero dispersion, slope for that S naught, and here the dispersion is around 3 picosecond per nanometer into kilometers. Slope. This is your lambda naught minimum. This is your lambda naught max. So here the dispersion is minus 3.4 kilometer into nan. So dispersion performance region is this. So any queries you can type in chat. I'll give you 5 minutes of time. Okay, thank you, Rakesh, for your feedback. Thank you, Sai Ganesh. So since there are no queries, on to the next topic, which is example of bandwidth single mode fibers. SM represents single mode. Graph is drawn for wavelength measured in for easier understanding versus the bandwidth utilized every gigahertz meter. For every kilometer, how much gigahertz is being utilized? So it varies from 1 to 10 power 4, 1, 10, 10 power 2, 10 power 3, 10 power 4. So everything is around cutoff wavelength. We are seeing 1310 nanometer. So when you convert that to micrometer, it is 1.3 micro. It is all around cutoff wave, or which has minimum. So this is for dispersion with 2 nanometer. This is for 4 nanometer. This is for 10 nanometer. And this is for 20 nanometer. This is for 40. This is for nanometer. So bandwidth will vary depending upon the mode of fiber that we are using and for what type of and its dispersion. So next is of wavelength measured in nanometer with respect to the mode field measured in micrometers, varying from 6 to 12. Okay, so you can see that it is around 1300 nanometer. Here it is lower. So this is the optimized 1300 nanometer curve. As the wavelength increases, you can see that the mode field diameter also tends to increase. So at this point, at approximately nearly 0.05 nanometer, the dispersion gets increased and it will the dispersion shift. So this is an illustrative graph for bending losses, bending that we had seen as a attenuation mechanism fibers. So when we are using a wavelength around 1400, I said that here 400 dispersion pattern gets increased or dispersion shifted. So at this point, you can see there is bending loss, more bending loss at 1400 nanometer. Okay. The reason why we don't use 1400 nanometer at all. So we are shifted 310 nanometer to 1550 nanometer, 310 nanometer to 155. So this is the reason. So when we use as the operating wavelength losses to micro bending and due to micro bending. When you do joining of two or more optical fibers, the micro bends will occur at the optical fiber. So, if 1400 nanometer, then obviously the 1400 nanometer will exhibit more losses due to bend. Okay, you can see this first one is your micro, one is your basic fiber loss. Okay, and this due to micro bending at 1570, 1560 nanometer. around the third window system. So in the physical connection, the macro bending has to be considered. Though the micro bend loss is very much less, I can see that it is nearly zero. You can see that 0.4 or 0.6 micro bend here, 0.6. So the macro bends are a major factor at this place. So the design of the optical fiber should be taking into elements. I see the bend effects on losses versus mode field diameter. So loss versus mode field diameter. Bending and micro bending. Mean square at around 2 nanometers. The bending loss is like that. At 10 micrometers, see that the mode field diameter will exhibit both the losses. The micro bending and micro bending will exhibit losses of approximately. You see. So which can next graph is bending loss for bend radius. So how if you bend a optical fiber with a radius of curvature, with respect to that, how much bending loss we get. So the effective bending radius measured in millimeters, varying from 12 mm to 24 millimeter. And the bending loss is measured in y-axis from 10 power minus 10 power minus 5. So you can see that here this is your 0 dB bending loss. You can see that bending loss varies drastically at this point. So dotted is your designed, this is your actual. Okay. Any